Dear students, today we will discuss on resistances connected in parallel and what is current divider rule. In the previous class, we have seen series connected resistors and numerical problems related to voltage divider rule. So we'll continue that analysis with the parallel connected resistors, so that by the end of this class, we should be able to determine the branch current and element voltages for, this one is parallel, for parallel combination of resistors using current divider rule. So parallel combination means, as we discussed earlier, that if there are two resistors available, if their start and terminals and end terminals are tied together, then it becomes parallel connection. And parallel connection will also provide the path for the current. Will also provide one second. Will also provide the path for the current. So current coming here will divide into the resistors. So here an example is given with the three resistors R1, R2 and R3 between the terminals A, B. All are connected between the same terminals A and B. Now voltage is also connected between A and B. This wire is not having any resistance. Okay, this wire. So it's nothing but this battery is also connected between A and B. So by seeing the circuit, we can say that voltage across R1 is V, voltage across R2 is V, voltage across R3 is V, and supply voltage is V. Same voltage is experienced by all the resistors when they are connected in parallel. But what happens to current? Let the battery give the current I. This current I is flowing like this. As there is a junction with the three resistors, this current will now divide into three currents. Let the currents be I1, I2, and I3 for R1, R2, and R3. Now, what is the observation here? Voltage across R1, voltage across R1 is V, and this voltage V should be equal to what? I1 into R1. Similarly, V should also be equal to I2 into R2. V should also be equal to I3 into R3. Okay. Now for parallel connected resistors, the current I, as it is dividing, I can apply the here at this point, I can apply KCL, Kirchhoff's current law. What is that one? Sum of incoming currents is equal to sum of outgoing currents. So therefore, I should be equal to I1 plus I2 plus I3. Now you see here. So we have written the current equations and total current. And I1 is nothing but what? V by R1. I2 is V by R2. I3 is V by R3. So therefore, you get I is equal to V into 1 by R1 plus 1 by R2 plus 1 by R3. Now this can be written as I by V is equal to this one, or V by V will be reciprocal of this one. Reciprocal of this, which is nothing but the equivalent resistance of the circuit. So what is the observation? If we have three resistors, or if we have resistors connected in parallel, they can be replaced by a single resistance RP or R equivalent. So 1 by RP is 1 by R1 plus 1 by R2 plus 1 by R3. And reciprocal of the resistance is nothing but what? Reciprocal of resistance is nothing but conductance. So for parallel connected resistors, total conductance of the circuit is equal to conductance of individual elements connected in parallel. G1 plus G2 plus J3 is G parallel. So what are the features of parallel circuits now? The observation made is voltage across each of the element is same. Current through any resistor is inversely proportional to its resistance. Then the total current in the circuit, the total current The total current in the circuit is equal to sum of the currents in parallel branches, and reciprocal of total resistance is equal to sum of reciprocals of individual resistances. For series connection, we had total resistance R equivalent is sum of the individual resistances. But for parallel connection, reciprocal of equivalent resistance is equal to sum of reciprocal of individual resistances, like this. So we can now see that the total current coming here is dividing into the individual currents for the elements, and hence we can use what is called as current divider rule. Okay, we can use what is called as current divider rule.